All right, so let's go ahead and take a look here at an example for number 1. We're being asked to simplify this thing. Now, the top is a monomial and the bottom's a monomial, so when you do that, basically you do it just like you're reducing a fraction. So you want to find something that goes into 36 and 81. I know 9 goes into 36 4 times, and I know that 9 goes into 81 9 times, and 4 and 9 can't be reduced anymore, so that's done. Then we also have the x cubed over x to worry about as well. We need to reduce that as well. And what you can do is you can think of that as x times x times x on the top, right? And then x on the bottom. And anytime you divide something by itself, x divided by x, they just become 1, right? And so what you're left with then is 2 x's on the top and 1 on the bottom there. So we have 4 with 2 x's on the top. And on the bottom we have 9 times 1, which is just 9. So there's our final answer for that. So basically just reducing is all we're doing on that first question. Let's go ahead and take a look at the next one. Next one a little bit trickier. First of all, on this particular problem, I noticed that I have y's in the top. I have 2 sets of y's, right? We're going to go and add those or multiply those together. Now the rule for multiplying works like this. If you have 2 exponential expressions with a common base being multiplied together, you could put them together with those exponents being added, right? So in this case, if I were to do y to the third times y to the third, what I would get is I would get y to the sixth. Because 3 plus 3 is 6. On the bottom here, we have negative 3 and an x to the negative third power, and we have an x to the positive third power. And so whenever I add x to the negative 3 with, whenever I add negative 3 to positive 3, I get 0. So I'll write this separately really quick to kind of show what I'm doing here. So I take the 2 x bottom there, multiply them together, and we get x to the 0. But anything to the 0 power is just 1. So basically, we're left with these things kind of just like canceling out. And so now all I'm left with then is with 2y to the 4th. Now, the next thing I want to do is I don't like having negative expressions that have negative exponents. And the rule for negative exponents is like this. If you have a negative exponent, it just makes it a reciprocal. Okay, so in this case, the x to the negative 3, I'm going to be moving that to the denominator, so it looks like this now. The 4 and the y to the 6th stay in the numerator, but now we have a 2y to the 4th on the bottom, as well as the x to the 3rd. That one went to the bottom because it was a negative exponent. After that, the problem becomes a lot like the first one I did. So before I go on to the next step, just review some things. You have 2 of the same variable on the top, go ahead and add their exponents. And when you have negative exponents, move it from top to bottom or vice versa to make it become a positive. All right, from there on out, the rest of it is to just do what we did in the last problem before this one, which is where you reduce. 2 goes into both of those. 2 goes into 4 twice. And it goes into 2 once, but we don't really need to write ones in the denominator. Next, we also need to do this. We have y to the 6th over y to the 4th. So what's going to happen is I've got 6 y's in the numerator, 4 y's in the denominator, and basically 4 of them are going to cross off and just become 1, right? But it will leave 2 left in the top. But we still have that x cubed on the bottom. All right, so there's that. Let's go ahead and move on to yet another, number 3 here. Now we've switched gears here. Every problem we've looked at so far has been a monomial. But as soon as you take 2 expressions like that, which is a monomial, I guess I could just put a letter here. As soon as you take one monomial and another monomial, and you add or subtract them, you end up with a polynomial. In this case, it's a binomial because there's 2 terms. So when you're dealing with binomials, trinomials, or whatnot with these fraction things is you've got to start by factoring. So to reduce these, the first thing that we're going to do is we're going to factor. After we've factored, we can go ahead and cancel out the factors that are the same on the top and bottom. So looking at the top, we're going to look to see how we can factor this. Well, the first thing we do is we always look for a GCF. I know that 6 goes into both of those numbers, 18 and 42. So I'm going to put 6 there. And I know I can also take out an n. So if I divide 18n squared by 6n, I'm going to be left with 3n. And if I divide 42n by 6n, I'm going to be left with 7. Next, on the bottom, we're going to do the same thing. We're going to factor this. In this case, it's another GCF question. So what goes into 12 and 54? Well, I know 6 does as well, right? So we have another 6 and n. So 6 goes into 12 twice, and 6 goes into 54 9 times. There's that. And then 6n divided by 6n is just 1. So what we're left with in the end then is just 3n plus 7 over 2n. So factor and cancel. Now just know that factoring sometimes could be different from one problem to another. These are both GCF problems, but don't forget, you could also have the box method if you have 3 terms, or it could be a difference of squares. Just keep those factoring strategies in mind. They could pop up. When you're multiplying two rational expressions, the steps are actually the same as the last one. We're just going to factor everything that can be factored, and then we're going to cancel anything that can cancel. So let's go ahead and take a look here. We have n plus 9 over... Now this bottom one we can factor with the box method there, so I'm going to do that over here on the side really quick. So we end up with n plus 9 and n minus 5. A lot of times it helps to put all the binomials in parentheses, even if they don't do that in the original problem. I would encourage you guys to do that. Now in this problem, actually, I didn't realize it till just now, but I actually didn't even need to factor, and I'll tell you why in a second, but for now, that top one is exactly the same as the other one, so of course they're going to factor the same. The reason why it wasn't necessary to factor is because, everything here cancels with everything here anyway. And so whether you factor it or not, that doesn't usually happen, just so you know, but in this case it did. So it was still good to demonstrate factoring using the box method. But in the end you can cancel. Now notice how I canceled, by the way, I took the denominator of the fraction on the left and I canceled that with the numerator of the fraction on the right. You're allowed to do that when it comes to multiplication, because when you multiply fractions, basically what happens is it just makes the whole thing become like one giant fraction, because you just do top times top and bottom. So it's, when you're multiplying, it's like they're all just one fraction anyway. So that's why it's allowed to cancel one thing from one fraction into another. Anyway, here's the rest of my answer. Now, at this point, some people may make a mistake. They may think, can't we cancel these things out? And the answer is no. I want to remind you guys of this little fact here. If you ever have a times b over a, those can cancel. But if you ever have a plus b over a, the a's cannot cancel. So this is a no-no, while this is open. And the reason for that is because fractions are basically division. You're dividing the bottom number into the top. And division does cancel multiplication. So since the a is multiplying the b, but the b is also being divided by a, you can just kind of let those a's cancel each other out. Whereas over here, the a is dividing a plus b. But on the top, the b is not being multiplied with a, it's being added with a. So these are not similar operations, so they don't cancel. Or I guess they're not, I should say they're not inverse operations. Anyway, so there's that. So this is our final answer for that one. Go ahead and take a look at the division problem. Division is a lot like the multiplication. It just has one extra step in the beginning. First of all, just so you know, if you ever see one that's not a fraction already, just go ahead and put a 1 under it so that it is a fraction. But anyway, step 1 is to do keep, change, and flip. So you keep the first fraction the same. You change your division into multiplication, and then you flip the other fraction over. Okay. Now after that, it's just another multiplication problem. So the rest of the steps match what we had in the last slide, which was factor and cancel. So on the bottom right here, I see that I can factor out an 8k, so I would rewrite this whole expression. And remember, when you're multiplying, it just becomes one giant fraction anyway. So this k minus 7 can cross off with that k minus 7. And what I'm left with on the top then is k minus 5. And on the bottom, I have 1 times 8k, which is just 8. And there's our final answer for that. So division is just like multiplication, just has this extra step here in the beginning of change flip. At this point, I'll review something else with you guys that's kind of important, although it doesn't seem to be coming up as an issue in this problem, but it could come up in the final or on your worksheet today. Remember this, is that a plus b over a plus b cancels because it makes 1, right? That's what we mean by cancel. They both make 1, right? In the same way, a plus b divided by b plus a still makes 1. It doesn't. The order doesn't matter. Okay. However, if you have a minus b over a minus b, those are exactly the same, so those make 1, right? But if you have a minus b over b minus a, those are not the same. Okay, just think about it. Like for instance, 5 minus 2 would not be the same as 2 minus 5. In fact, we can demonstrate something here. They do come out to be the same number, it's just their opposite signs. So they make 1, but they make a negative 1. So if you're ever doing a problem where you have two factors that look like this, same thing, they're both subtraction, but the numbers are just reversed, go ahead and cross them off, but don't forget to put a negative in front of the whole answer that you have, because it makes the whole thing become negative. So keep that in mind. Could pop up. Let's move on to these guys here. These are what are called complex fractions. Complex fractions are basically just another way of writing a division problem because you have the top being divided by the bottom. So the first thing you want to do with these is just change it into a division problem. After that, you're going to follow the steps for division, which are keep, change, flip, factor, which in this case we're dealing with monomials, so there's no factoring for this one. And then we just go ahead and multiply straight across, and what we're going to end up with then is 27 over 25x, and nothing reduces there, so we're good to go. But don't forget, when it comes to monomials, if you can reduce the fraction, go ahead and do so. Okay, we're going to switch gears here for a second, talk about adding and subtracting rational expressions. So in order to add or subtract rational expressions, you need to have a common denominator. So our first few problems are going to start off with common denominators, and then we'll show what to do if you don't have a common denominator. All right, so first of all, we have u minus 3v over 10v. Now, since these things have a common denominator already, we're just going to apply that negative there to that 5 and put it there. And we could just put these fractions together, so it's top minus top, just like that. From there, if we could, we would factor or reduce if possible, but in this case, we can't really combine anything together. We can't simplify that, so that one's actually done. It's kind of a silly question, honestly, but it is what it is. Let's go ahead and take a look at another one. Here's another one. In this case, once again, we have a common denominator. So when you have a common denominator, you just do the top on the left, parentheses are good to have, plus the top on the right. Now remember, if you're subtracting here, which we're not, but if we were, you would distribute that in, okay? So keep that in mind. Oops. So in this case, though, I'm adding, so we're not going to be distributing the negative in. And the bottom is just 20x. Okay, so we will just combine our x's together, so I get 2x. We'll combine our y's together. Positive 5 take away 3y is going to be positive 2y. And that's basically it. But in this case, we can reduce this expression. So we're going to treat this like reducing polynomial or rational expressions with polynomials, right? So the first step is to factor. Now, I'm not going to factor on the bottom and all, but on the top, we can factor that. We can see that a 2 comes out of there. Now, this 2 and this 20 can be reduced, right? 2 goes into 20 10 times. So we're left with x plus y over 10x. That's our final answer. So basically, the big gist of it is that when they have a common denominator, just add the tops together with that common denominator. If possible, factor and reduce at the end. You'll find that it's not always possible to reduce these things. Something you check for. If you can, do it. If you can't, don't stress about it. Now we're going to move on to another problem. For this particular problem, we do not have the same denominator. I'm going to give you guys two problems like this, though. In this case, we have monomials in the denominator. But in the next example, it's going to be binomials. And the way that you handle these is different. So let's see how you start by handling monomials. Well, basically, you just need to find the common denominator here. So let's start off with 4 and 3. What's the common denominator for 4 and 3? Well, it's 12, right? So let me write this out really quick. Copy the problem a little bit bigger here. Okay, well, we already know the common denominator for 4 and 3 is 12, right? So I'm going to multiply this side by 3 so that I get 12, right, on the bottom. And by the way, don't forget to put your binomials in. And on this side, we need to multiply the top and the bottom by 4. Right? But we have letters here that we need to get. Notice they both have a B, so we don't need to put B's on either side. They're both matching there. But this one over here on the left has an A squared. So this side over here also needs an A squared, so it looks like the other one. So we're going to multiply A squared to the top and bottom. Okay? Once you've done that, you're going to go ahead and multiply in. So you're going to have 3A plus 3B over, this is going to become 12A squared B plus, putting these together, we're going to get 16A squared B. And on the bottom, we have 12A squared B. And now that we have a common denominator, we're just going to add the tops. Now notice there's no like terms there, so we'll just put them all together on the top like this, with that one common denominator. And that top expression is not going to factor. So the only thing you could try if you wanted to would be the box method. I already know that's not going to work. I'm not going to waste my time, but there it is. Most of the time, you guys, just so you know, when they start off with uncommon denominators, after you've gone through all this mess of getting them to be the same, you end up with such a weird expression that it can't be factored, and therefore it can't really be reduced. All right. Now, when it comes to having polynomials in the denominator, the process is a little bit different. If possible, you want to start by factoring. So that's step one, is to factor if possible. Now, in my problem, these don't factor. B plus 6 and b minus 5. You can't do anything with those. But once you factor, you're going to go ahead and match the denominators up. So anything that is on the left side, so that's where I'll pick up on this particular problem. So I have 4 over b plus 6 minus 6b over b minus 5. So this side has a b plus 6, this side has a b minus 5. So to get these two sides to match, I'm going to do a b minus 5 over here. And whatever you do to the bottom, of course, you do to the top, right? And this side over here needs to have a b plus 6 added to it. All right, the next thing we're going to do is you're going to multiply in the numerators. Means the top, right? So I'm going to multiply here. That's a distribution in this case. So that's going to end up being 4b minus 20. And same thing here, we're going to distribute again. And we're going to get 6b squared plus 36b. My b's and 6's look a little similar there. I have to be careful. Then on the bottom, we still have b minus 5, b plus 6. Okay. Now what I'm going to do is I'm going to combine them. So step 4 is to combine the numerators. Now in this case, since I have a subtraction sign here, I'm going to be distributing that into the top. Okay, so I'm running a little bit out of space here, so let me make some space for myself. All right, so distributing that negative on the top then and putting them together, we're going to have the following. We're going to have 4b minus 20 on the left. And distributing the negative in, we end up with minus 6b squared minus 36b. And on the bottom, we have the common denominator that we So, combine any like terms that you may have, like 4b and negative 36b, those can be put together. And I also like to put my terms in order, so I'm going to put the negative 6b squared in the front here. And then the 4b and the negative 36b combine together to make negative 32b. And then finally we have negative 20. And like I said, it's pretty rare that this is going to reduce after all this work. I'm pretty sure we're not going to be able to do anything on the top here. I just out of curiosity, I think I'll give it a try. I know that 2 goes into all 3 of these numbers here, and also they're all negative. So I'm going to take out a negative 2, which I'm just going to show my work here on the side. But I'm pretty sure this is not going to end up being factorable, just so you know. I'm just trying it. Oops. And then this is a box problem, which I'm pretty sure is not going to work, but let's try it. No, it's got to be 3b and b there. 5. So this makes 6b and this makes 5b. So 6 and 5 can't give me the middle, so that's not right. I could try switching the 2 and the 5 around. Putting the 5 here and the 2 here. Let's try that out and see how that works for us. That's going to give me 15b and 2b. 15 and 2 can't make 16 either. So let's go ahead and try, oops, too far. So I know it's got to be 3b and b. I can't change those. That's the only possibility to go there. But something else we could try is 10 and 1 for the last number there. That's going to be 3b and 10b, which can't make 16 either. Now, if I switch the 10 and the 1, I'm going to end up multiplying 10 by 3, and that's going to give me 30, and that's way too much. So, like I suspected, this thing is not factorable. Kind of tried all the possibilities there, and we'll just leave our answer just like this. Move on. So now that we've learned how to add and subtract, we're going to come back to our complex fractions here for a second. First of all, what we want to do is we want to simplify either the numerator or the denominator if it has more than one fraction. So in this case down there we have 2 of those things being added together. Now in this case I got a little bit lucky. I'm not sure what you guys will see on yours, but I know that on mine I've already got common denominators, so that's kind of nice, which means that all I need to do is take this minus and distribute it here, that common denominator, and then those combine to make that cancel out, and we're left with just 1 over u plus 4. So I'm going to rewrite this whole expression now. Top, we haven't done anything with that, so that's going to stay just like that. But I got the whole bottom here to become 1 over u plus 4. Now, once you have done that, using your steps for adding, you're going to go ahead and follow the steps like we learned earlier for dealing with complex fractions, which is to rewrite it as a division problem. And then do keep, change, flip. And then multiply straight across. Now, technically, it would be maybe okay to leave it like this, but I'm pretty sure that on the answer key, they're going to go ahead and ask us to multiply that out. So I'm going to go ahead and do that really quick on my answer key. Let's see, we have u minus 1 and u plus 4. So, write that out. We have u squared. 4u, take away 1u is going to be 3u. And then we have the minus 4. And on the bottom, we still have a u. And there it is. So, complex fractions where you have to add or subtract before you actually do the keep, change, flip. Okay, that's another one. Let's go ahead and take a look at some other types of questions here. On this one, it's asking us to state the excluded values. Some functions have excluded values, and what that means is there's certain values that x is not allowed to be equal to. There's a couple of functions like that. Logs are like that. Rational expressions like this one are like that, and square roots are like that. Some functions you're just not allowed to plug in certain things, otherwise you get wacky things happening. Well, when it comes to rational expressions, the excluded value is any value of x that makes the denominator equal to 0. Okay, so in this case, if I let 49x squared plus 42x equal 0, and I solve for x, whatever I get, that's going to be an excluded value. Now, this is a quadratic, so to make things really complicated, you could use the quadratic formula. I think you wouldn't like it. Those numbers are really big, crazy numbers. All the questions I'm going to be giving you, though, can be solved in another way, which is by factoring. So, in this case, I can factor. What goes into 49 and 42? Well, that would be 7. Also, they both have an x, so I can take an x, which gives me this. After you've factored the denominator, you set each piece equal to 0 and solve. So 7x equals 0, and 7x plus 6 equals 0. And then you solve both of those. If I solve this one, I'm going to end up with 0. And if I solve this one, I'm going to end up with negative 6/7. So these are the two excluded values. In other words, these are two values of x that you're not allowed to plug in for x. Because if you did, it would make the denominator equal 0, which isn't allowed. So these are what we call the excluded values. So basically, set the denominator equal to 0, factor, and solve. So we keep that in mind because when we're solving equations like we're going to be doing for the last few problems here, is that it's possible that when you're solving an equation that involves rational expression, it's possible that you get an answer that's an excluded value and you have to say, oh, I have to throw that answer away because that's an excluded value, therefore there's no solution. But we'll see how that goes. All right, so step 1 for these when it comes to solving rational equations is you want to, let's see, factoring the denominator is usually the first thing, but we're dealing with monomials, and when it comes to monomials in the denominators, you don't factor them. So we won't be doing step 1 on this particular problem. Step 2, however, we will be doing, and what you do on step 2 is you multiply the denominators all the way across. So what do I mean by that? I'm going to multiply all 3 fractions by the denominators. So one of my denominators is 2n, so I'm going to multiply everything by 2n. Now why do I do that? Well, because if I multiply 2n to the top of this fraction, those cancel. And now I don't have a fraction anymore. Now over here, nothing really cancels, so I'm just going to go ahead and do my multiplication. 2n times 1 is 2n. Same thing here, nothing really cancels. We end up with 4n over 3. And now we just repeat that process. So now I want to get rid of, let's say, the 6. So now I'm going to multiply everything by 6. So times 6, times 6, times 6. And for this one, the 6's are going to cancel, and I'm going to be left with 2n. Over here, however, nothing cancels. So it's just going to stay like that. And here, nothing cancels, so I'm left with 24n over 3. Now, I could just repeat this process a third time to get rid of the 3, but something that you may notice as you go along, and we actually could have done it earlier as well, but something you may notice as you go along is that instead of multiplying by 3 again, sometimes it just divides into a nice number anyway. Like, what's 24 divided by 3? Isn't that just 8? So I can just do that and not have to worry about doing another multiplication. Okay, so if you notice something like that, go for it. But if you went through and multiplied by 3, it would be totally fine. Now, the next thing we do is distribute. Find your like terms. And solve. So I've got 24 on the left side and 4n on the right. So division gives me 6. So after you multiply the denominators out, you basically just have to solve what's left. Let's go ahead and, I guess though step 4, we should check our answers. It should not make the denominator equal 0. So if we come up here to the original problem, there's only one place where I can plug my answer, 6, into a denominator, and that's right here. If you plug in 6, what's 2 times 6? 12, right? That's okay. We're good. We're happy with that. But if you ever get an answer and when you plug it in, it makes one of the denominators equal 0, then we would have to throw that answer away and say that's an excluded value. Therefore, there's no solution. But in this case, 6 is not an excluded value. Therefore, this is my answer to my equation. Let's do another one. All right. Now, in this case, I have polynomials in the denominator instead of monomials. And so in this case, we will be doing that first step, which is to factor. I'm going to write my steps up here again. So this one doesn't factor, so this fraction is going to stay the same. And notice we only factor the denominators. We do not factor the numerators. We could, but it won't help us at all. It'll actually make things harder. This one does factor. I can take an a out. If you take an a out, you're left with this. Same thing on the other one. Okay, once you do that, you're going to go ahead and start getting rid of stuff. So now I'm going to multiply the denominators out, right? So I'm going to multiply 3a plus 4 here, here, and here. So that cancels that. This cancels this. This cancels this. And let's see what we have as a result now. We have 4 equals 3a minus 15 over a plus 4 over a. Get to go ahead and multiply one more time now. So I'm going to multiply by a times a and times a. And on these last two, the a's go away. And we're left with 4a equals 3a minus 15 plus 4. Okay, so from there, we factored, we multiplied our denominators, now we just have to solve. So I'm going to subtract 3a on both sides. So subtracting 3 over here gets rid of the 3a. And subtracting 3a from 4a leaves us with 1a. And on the right side, we have the negative 15 and 4, which can be combined to make negative 11. Once again, we want to make sure that doesn't make any of our denominators equal 0. You don't actually have to plug it in. You can kind of just eyeball it. But I mean, if you guys think about it, plugged in 11 here, is that going to make 0? No way. 11 squared is 121. If you multiply that by 3, you're going to get a really big number. And you're going to add even more to it after that. So, well, actually, it's negative. So it'll take some off, but it's not going to make it equal 0. And if you just want to double check, you can. But I can tell you right now, if you plug in 11, you're not going to get 0. So that's that. So our answer is negative 11. Okay, one more problem. I think. No. 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 One more problem. All right. So same thing. We want to start by factoring. So these do not factor, but this one does. Now to save me some work, I already know that one of them has to be k plus 6, because if it wasn't, then we're going to have trouble getting them to match. It's not always like that, but it's pretty much a guarantee. So Sure enough, 6 and 6 make 12, so we're good. So here is the factored form. And the only difference in these denominators is the fact that we have to multiply. This one has 2k plus 6 down there, right? So let's get to work. So we're going to start by multiplying everything by k plus 6. And that leaves me with 1 plus 2k minus 3 equals k minus 1 over k plus 6. Okay, we're going to multiply by k plus 6 again. Okay, so these cancel, and I'm left with k minus 1 over here. Now on this side, nothing's canceling, right? So I'm just going to put these next to each other like this, like a multiplication problem. Multiplication. And then here we're multiplying k plus 6 times 1. So you can write it like this if you want to, but anything times 1 is just going to be itself. All right. So now after this we solve, right? But this was a little bit more complicated. Well, first of all, let's uncomplicate it. Let's multiply these things together. So I'm going to multiply this in like this, and I get k plus 6. Right? Plus, well, this is a box problem, so I need to do the box multiplication method to get that. So here we go. We have k plus 6 and 2k minus 3. So we have 2k squared, negative 3k, and positive 12 makes positive 9k. And then we have negative 18. All right, continuing on. So now on this side, I want to start putting some stuff together. Like I could put this k and this 9k together. The 2k squared is not going to change. But k plus 9k is going to be 10k. And then 6 and negative 18 can make negative 12. Now, what we're looking at here is a quadratic equation. So when you have a quadratic, the way you solve it is a lot different than when you're trying to solve a linear equation. So there's two ways you could solve it. One is by factoring, and the other is by using the quadratic formula. But either way, before you can do either of those methods, is you want it to equal 0 first. So what I want to do then is I want to move this k out of here, so that cancels. And whatever you do to one side, you do to the other, right? And I also want to get rid of this 1, so I'm going to add 1, causing those to cancel. So we'll add 1 on this side also. So now we have 2k squared plus 9k minus 11 equals 0. Now it's ready to be solved using either factoring or the quadratic formula. Just so you guys know, every problem I'm going to give you for this sort is going to be a factorable problem. And that's the method I'm going to go with. I don't prefer the quadratic formula, but the quadratic formula works. So you're welcome to use it if you remember it from our previous review lessons that we've worked on. But like I said, I'm going to go ahead and do factoring. So here we go. That's going to be 22 and 1. That's not going to work. back up a little bit. Oops. The 11 here instead of the 1 here. That'll work. Hit my negative. So this thing factors into 2k plus 11 and k minus 1. And then you just solve both of these, right? You're going to do 2k plus 1 equals 0 and k minus 1 equals 0. And you solve both. So for this one, if you solve, you're going to get k equals 1. And for this one, if you solve, you're going to end up with k equals negative 1. And once again, you just want to make sure it doesn't make the denominators equal 0. And neither one of them do in this case, so they're both good answers. Sometimes when you end up with two answers, one of them could be an excluded value, but the other one's a good answer, right? That could happen. Or they could both be excluded. That's another possibility. But in this case, they're both good. If you plug in a negative half, that's not going to make this equal 0. Same thing for 1. And this one here, it's really just the same thing twice, right? So plugging either of those numbers into that is not going to make this equal 0 either. So we have good answers, and those are it. And that closes us out for this particular review. So until next week.